Hello, welcome to my channel. My name is Putu Arindra with my stand number 230553171, and this about learning material about mechanical property and strengthening mechanism. Okay, my main reference is a book from Metallurgy for the non-metallurgy. Okay, we just next to 3.1 mechanical properties. When a force or combination of force are applied to a material, the material responds by deforming and straining, often in a complex manner. For example, when a buggy jumper hops off of a platform, the buggy causes stress dramatically, and at the same time, its cross-sectional area decreases. Under normal circumstances, the buggy cord safely prevents the jumper from hitting the ground below. While this example describes a type of deformation that is readily visible, often deformation of this type cannot be observed this easily, but it does still take place. For example, a weak hub from the end of a steel wire will cause the wire to stretch and its cross-sectional area to decrease, but the amount of deformation is not readily observed without performing carefully measurement of the length and diameter of the wire under load. Mechanical property describe the relationship between a stress acting on a material and the resulting deformation the material undergoes. As a result of this applied stress, the concept of stress in its most general form is a force or load divided by the area over which it acts. For a force F acting over an area the stress sigma is sigma F per A. Stress is often expressed in unit of MPa, or equal to 10 to the 6 Newton meter, or KSI equal to 10 to 3 pound inch. There are two general methods used to characterize the stress: engineering stress and true stress. Engineering stress is the most often used in engineering design calculation, and it based on the original cross-section area A0 of the part of component under consideration. Because engineering stress is based on the original cross-section area, it does not take into consideration the fact that the cross-sectional area changes when a load is applied to the material. While the material is under load, the resulting change in cross-sectional area depends on the material property and the magnitude of the applied stress. True stress is based on the instantaneous cross-sectional area under load, and is therefore a more accurate method for characterizing the stress. Because the value of the true stress is typically more difficult to determine than the engineering stress, it is useless frequently in practice. Strength allows us to quantitatively characterize the deformation that occurs due to the application of the applied stress. It should be noted that strength is pure number. It has no unit associated with it. To calculate the strain, the original dimension or shape of the underformed body is compared to the same dimension or shape in the deformation body. The method used to calculate the strain has the same unit in both the numerator and the denominator, and so this unit cancel each other out, resulting in a pure number. Example are provided subsequently is illustrate how to perform this type of calculation in a simple tension test. In the conventional engineering tension test, an engineering stress strain curve is constructed from the load elongation measurement made on tensile test specimen. It is obtained by defining the load F by the original area of the cross section of the specimen A0 sigma F per A0. As a tension on the test specimen increase, the gauge length change in response to the applied stress. The resulting strain depicted in the engineering stress strain curve in the average or nominal linear strain, which is obtained by dividing the change in the gauge length, or also called the elongation of the specimen by its original length. L0 epsilon delta per L0 equal delta L per L0 equal L per LO per L min LO per LO. Because both engineering stress and the strain are obtained by dividing the load and elongation by constant factor, the load elongation curve has the same shape as the engineering stress strain curve. The shape and magnitude of the stress strain curve of a metal depends on its composition, heat treatment, priority history of plastic deformation, the strain rate, temperature, and the state of stress imposed during the testing. Material properties are often determined by performing mechanical measurements such as the tensile test described previously. The parameters that are typically used to describe the strain test stress strain curve of a metal include the tensile strength, yield strength or yield point, percent elongation, and the reduce in area. Different type of tests which use an applied force can be employed to measure the other mechanical property as well. Additional example of such property include the elastic modulus, hardness, fatigue resistance, and the fracture toughness. They are described subsequently in more detail. A short list of important types of mechanical property include: first, hardness as a measure of resistance to the tension. Second, linear elastic constant that relate the strain under tensile, comprehensive, and shear load. Third, yield strength, indicating the stress level required for the onset of permanent deformation. Fourth, ultimate strength, indicating the maximum engineering stress that the material can withstand without fracture. Ultimate tension strength typically is associated with the onset of necking tension test specimen. And the next, fatigue strength, indicating the level of cycling stress that causes fracture due to metal fatigue over time. Next, impact crudeness, indicating energy absorption from load that cause very high strain rates. Next, fracture toughness, indicating resistance to fracture with resisting flow or stress raise in the geometry of a part. In the next, high temperature creep deformation and stress rupture, where high temperature cause metal to permanently deform as a function of time. Next, damping property, and the last one, were resistant property. Okay, next, elasticity. In the elastic region of the engineering stress strain curve, stress is linearly proportional to strain. This region in the strain line that can be seen on the left hand side of the stress strain diagram. When a crystal is stressed by an internal or external load, the lattice strain in the response to applied stress through the relative movement of the atom. When the load is removed, the crystal or object will return to its original size and shape, provided that all the bonds between the atom in the crystalline lattice are not stressed to fall. When this previous is met, the strain is elastic, and the amount of strain is directly proportional to the amount of stress placed on the crystal or object. This law proportionally is called Cauchy law. The linear relationship between applied stress and elastic strain results in a physical property called the modulus of elasticity of the material. The modulus obtained under axial tension or compression loading is called Young modulus and is represented by E, such that sigma equal E times epsilon, as the sigma is the stress and the epsilon is the strain deformation per unit length. The value of the elastic moduli are primarily determined by two fundamental contributing factors: the crystalline structure of the material in question and the atomic bond strengths. The elastic module tend to be highest in the material with strong bonding, and the lowest is polymer. Tensile modulus range from about 15 GPa for lead to over 400 GPa for tungsten. The elastic constant under tension or shear loading in the modulus of rigidity or shear modulus G, Young modulus, and the shear modulus are related by the formula below, which involve Poisson ratio, defined as the ratio of lateral strain to axial strain in a stressed material. There is V equal E minus 2G per 2G. The shear modulus G of pure material is consistently about 3 per 8 that of the tensile modulus. Hydrostatic compression causes material to contact in volume. The ratio of the unit change in volume to the mean normal comprehensive stress is called the compressibility beta of the material. The inverse of compressibility is called the bulk modulus, or K, of the material. In mechanical design, the stiffness or rigidity of a part is related to its section thickness, and the elastic modulus were designed to limit or control elastic deflection. A high modulus material of the same physical dimension will deflect less than low modulus 1. Unlike strands, the elastic modulus of metallic material are very difficult to change by changing the composition or heat treatment. This can be important if higher strengths allow weight reduction with reduced section thickness. If the elastic constant of the strong material does not compensate for the reduced stiffness due to reduced section thickness, this could adversely affect the stiffness of the component. It is also important to note that for some alloy, the elastic modulus does change with the level strength. Okay, next, plasticity. Plasticity, the point at which plastic deformation or yielding is observed to begin depends on the sensitivity of the strain measurement. With most material, there is a gradual transition from elastic to plastic behavior, and the point at which plastic deformation begins is difficult to define with precision. In the test of material under anexial loading, three criteria of the initial of yielding have been used. That's the classic limit, the proportional limit, and the yield strength. With increased sensitivity of strain measurement, the value of the elasticity limit is decreased until it equals the true elastic limit determined by microstrain measurement. With the sensitivity of strains typically used in engineering studies, the elastic limit is greater than a proportional limit. Determination of the elastic limit requires a tedious incremental loading-unloading test procedure. The critical stress for one set of permanent deformation is difficult to determine precisely because the elastic limit is so low in the most metals. It also varies among testing devices and is sensitive to machine stiffness. Precise measurement of the elastic limits for material is often determined instead by a sonic vibrational test, not by a stress strain curve. The elastic limit is often replaced by the proportional limit. Offset yield stress determination requires a specimen that has been loaded to its 0.2% offset yield stress and unloaded so that it's 0.2% longer than before the test. The offset yield strength is often referred to in Great Britain as the proof stress, where offset value are either 0.1 or 0.5%. The yield strength obtained by an offset method is commonly used for design and specification purpose because it avoids the practical difficulties of measuring the elastic limit or proportional limit. This definition makes the yield strength a much more appropriate criteria on which to base design consideration. The yield strength is necessary is estimating the force required in forming operation. Most structures must be designed so that a forcible overload does not exceed the yield strength. When the stress exceeds a value corresponding to the yield strength, the specimen undergoes gross plastic deformation. If the load is subsequently reduced to zero, the specimen will remain permanently deformed. The stress required to produce continued plastic deformation increase with increasing plastic strain, that is, the metal strain hardness. The volume of the specimen remain constant during plastic deformation. AL equal A0 L0, and as a specimen elongates, its cross-sectional area decreases uniformly along the gauge length. Initially, the stress hardening more than compensate for the decrease in area, and the engineering stress continues to rise with increasing strain. Eventually, a point is reached where the decrease in specimen cross-sectional area is greater than the increase in deformation load arising from strain hardening. This condition will be reached first at some point in the specimen that is slightly weaker than the rest. Alveolar plastic deformation is concentrated in this region, and the specimen begin to the neck or thin down locally because the cross-sectional area now is decreasing far from rapidly that the deformation load is increased by strain hardening. The actual load required to deform the specimen far off. The amount of deformation before fracture is a measure of material ductility, which also relates to the toughness of a material. Brittle material typically fractured suddenly with little or no plastic deformation. Brittle metals such as chromium, for example, will fracture upon loading the elastic limit rather than sustain plastic deformation. In contrast, ductile material can exhibit a large amount of plastic deformation before fracture. Upon loading of ductile material beyond the elastic limit, the additional of plastic deformation to the elastic strain causes the total strain to increase at a faster rate than before, and the plot curve off from the modulus line. It should be remembered that engineering stress is normally the normal stress rather than true stress. In the initial portion of the plot, the amount of lateral contraction of the specimen is distributed along the entire test length, or the specimen, and is therefore so small that the nominal and true stress are almost identical. But it's the latter portion of the test, making of a tensile specimen occurs, that is, training begins to concentrate in the region where fracture will eventually occur. This necking can often become so pronounced that the nominal stress will decrease upon additional loading, even though the true stress continue to increase until fracture occurs. Nominal tension stress versus the strain is sometimes called an engineering stress-strain curve. To distinguish is from a true stress-strain curve. The high point on an engineering stress-strain curve is defined in test standard as the ultimate tensile strength of the specimen, or simply the tensile strength. The point of fracture is called the fracture strength or breaking strength. Upon fracture, the elastic energy in the specimen is released and the elastic strength is recovered. The plastic strength remaining the specimen called the total elongation is determined by fitting the broken piece together and measuring the new distance between the gouge mark. The reduction in area of a broken specimen is determined by measuring the dimension of the neck-down region, the fracture, and comparing that cross-sectional area to the original cross-section. So material have essentially no linear portion to their stress-strain curve. For example, soft copper, gray cast iron, and many polymers exhibit this characteristic. For this material, the offset method cannot be used, and the usual practice is to define the yield strength and the strength required to produce some total strength. For example, E equals 0.005, and other time the slope of the stress strain curve is described by plotting the Session modulus or the tungsten modulus. So metal, particularly annealed low carbon steel, did not have a gradual transition from elastic to plastic behavior. Instead, the yield point fluctuates about some approximately constant value of load and then rise with further strain. The load at which the sudden drop occurs is called the upper yield point. The constant load is called the lower yield point, and the elongation that occurs at constant load is called the yield point elongation. The stress at the upper yield point rather than the lower yield point is usually reported as the yield strength of this material. Yield point elongation of low carbon steel is due to discontinuous deformation in that one or more decreased deformation bands known as ladder's line, ladder's band, or stretcher strain propagate at various positions along the length of the tensile specimen. This band from at angle approximately 45 to 55 degrees to the stress axis. At the upper yield point, this discrete band deform starting at a stress concentration such as a fillet. Coincident with the formation of the band, the loads drop to the lower yield point. The band then propagates along the length of the specimen, causing the yield point elongation. A similar behavior occurs with some polymers and superplastic metal alloy, in which a neck from bud grow in a stable manner, with material being fed into the neck's region from the thicker adjacent region. This type of deformation in polymer is called drawing. Next, creep deformation. Creep deformation refers to the time-dependent plastic deformation that occurs when a material is subject to constant nominal stress. The rate of creep deformation depends not only the magnitude of the applied stress, but also on time and temperature. Continuing creep deformation over time ultimately leads to creep rupture, also known as stress rupture. Creep deformation of metal is typically a high temperature phenomenon. Also, the temperatures required are relative to the melting point of the alloy. Metals do not exhibit creep deformation until the temperature approximately 0.3 to 0.5 km or degrees Kelvin. This behavior is associated with a weakening of grain boundaries at higher temperature. At low temperature, grain boundary regions are stronger than grain, and thus deformation occurs by slip and planing within the crystal structure of grains. This type of plastic deformation is stress dependent. At sufficiently high temperature, however, grain boundaries become weaker than grains. Atoms in grain boundaries at high temperature become more susceptible to diffusion, and thus atomic restructuring within grain boundaries become much more active as a function of not only stress, but also time and temperature. This creates conditions for creep deformation. Metallurgists in the early 1900s also defined a temperature at which the strength of the grain and the grain boundaries are equal. It is called the equicohesive temperature, or ECT. The ECT is affected by material characteristics and the loading condition. There are many variables that affect the ECT, and the quantification of an actual temperature is possible for only a specific set of conditions. The usefulness of the ECT in practical terms is limited. Most creep testing is done under tension and at elevated temperature. The initial rate of creep strength upon loading is fairly rapid, but decreases with time. This is called primary creep or stage 1. The creep rate then reaches a steady state, which is called secondary creep. In third stage creep or tertiary creep, the creep rate begins to increase again and continues to increase until the specimen breaks. The relative portion of the total time to rupture taken by these three stages depend on the several factors. Value of strength and time are typically plotted on a log-log scale in creep diagram. The result of creep tests are reported in a variety ways. Sometimes the result for a given temperature are reported in the form of isochronous stress strain curve, with a curve constructed from equal time points on the stress strain relationship determined in the creep test. The elastic portion of such isochronous stress strain curve is added by using the modulus value for the test temperature determined independently. The stress that causes a specified strain at the temperature is then called the creep stress of the material for those conditions. Other times, equal strength results for a given temperature are plotted on the stress time graph. When a creep test is continued until the specimen rupture, the test is often called a creep rupture or stress rupture test, and the results are reported on a plot of stress versus time to rupture. Okay, we next to fatigue. The tendency of a material to break under condition of applied cyclic stress is called fatigue. Fatigue fracture are different from the ductile fracture that usually result from regular tension and creep loading of the mass material. Instead, fatigue fracture is caused by the propagation of crack that initiate at a single point or at a few points in the material, and the fatigue fracture are almost always brittle fracture. Most part and fatigue specimens contain points of stress concentration, such as surface roughness or change in the part of specimen section, at which stress is considered, and when fatigue cracking initiates, the amount of concentration can be determined and is reported as the theoretical stress concentration factor or simply the stress concentration factor. The fatigue stress reduction factor or fatigue nodes factor can be determined by dividing the fatigue strength of smooth specimen by the fatigue stress of nodes specimen. Comparing the fatigue stress reduced factor to the theoretical stress concentration factor give a measure of the sensitivity of the material to nodes when under cyclone loading. Node sensitivity is the fatigue factor defined by the KT min 1 and often is expressed as a percentage. Several different fatigue tests have been deployed. Is designed to replicate the loading condition found in specific industrial application. The rotating beam test replicates the loading of railroad axle. The plate bedding test, a link spring, the axial test, connecting rods and chain link. Some tests run under constant load, while other run under constant strain. Therefore, tabular value of fatigue strength or fatigue limits are of value mainly in material selection, rather than useful in actual design calculation. The stress in fatigue test usually is cycled between a maximum tensile stress and a minimum tensile stress, or between a maximum tension stress and a maximum compressive stress. The ratio of this extreme is called the stress ratio. The ratio for fully reversed stress then becomes -1. Other terms used to describe fatigue stress include mean stress, the stress range, and the stress amplitude. The result of fatigue stress are usually reported in the form of plots of stress versus number of cycles to fracture, called SR curve. In this plot, the number of cycles is usually plotted on a logarithmic scale. Most metal have SN curve that continually show longer life at lower stress, and the fatigue strength of the material must be recorded for a given number of cycles. For steel, however, the curve breaks off and become essentially horizontal at some stress level called the fatigue limit. Okay, we next to toughness. Toughness is the ability of a material to absorb an impact or shock load without fracturing. Specimen and notch geometry as well as the manner of load application are all important in toughness determination. For dynamic loading condition and when a notch is present, notch toughness is assessed by using an impact test, such as a crappy impact test. A special measure of toughness called the plane strain fracture toughness, and it uses linear elastic fracture mechanics to characterize the resistance of a material to the onset of crack propagation when a exciting crack is represent in a material when the stress intensity factor that describes the state of stress at the tip of crack of nozzles and geometry exceed the plane strain fracture toughness of the material crack propagation will result. The amount of ductility is also related to the toughness of a material. For the static situation, toughness can be determined from the result of tensile stress test. It is related to the area under the stress-strain curve up to the point of fracture. The material can accommodate greater amounts of strength than brittle material. Next, hardness. Hardness is the resistance of the material to plastic indentation. While the measurement of hardness can involve only a simple stress test on a bond stress, it usually involves the amount of indentation caused by the application of the hard indenter of some standard shape and material. Hardness value are roughly proportional to the stress of a metal. Therefore, hardness value can be useful during selection of a suitable material for an application. Hardness value are very useful during quality control operation. Okay, we next to 3.2 strengthening mechanism. Strengthening mechanism. Next, 3.2.1 solid solution strengthening. Solid solution strengthening is a mechanism that increases the strength of a metal through the careful addition of a specific alloying element. The insertion of substantial and or interstitial alloying element produce a strength in the crystalline lattice of the host solid structure because the solid atom typically have a different size than the host atom. The resulting distortion or strain energy creates a barrier to this dislocation motion. As a result, moving dislocation in either attracts to or repelled by the solid. However, both situations result in a strength increase. When the dislocation is attracted to a solid, the additional force required to pull the dislocation away from it is the cause of the edge stress. If the dislocation is repelled by the solid, an additional force is required to push the dislocation past the solid atom. Types of solid solution hardening indicate the amount of hardening depends on the relative difference in elastic stiffness and atomic size between the solvent and solid. In general, large difference result is greater strengthening, but at the same time, the greater the difference is size between the solid and solvent atom, the more strict is their mutual solubilities. The solvent phase becomes saturated with the solid atom and reach its limit of homogeneity. When the distortion energy reaches a critical value determined by the thermodynamics of the system, nickel and zinc atoms are about the same size as copper atom, but beryllium and tin atom are much different in size from copper atom. Increase the atomic size difference and the amount of alloying both result in increase in solid solution straining. Okay, we next to 3.2.2 effect of grain size. Grain boundaries are effective obstacle to slip because the slip of dislocation in the lattice of individual grains cannot easily cross the high energy barrier of the grain boundaries. Instead of dislocation are blocked by fill up at the grain boundaries. Thus, grain boundaries provide a sort of straining by pinning the movement dislocation. Smaller grain in a polycrystalline material also mean that greater percentage of the material constant of grain boundaries for straining. The exception are when grain boundaries become weakened to environmental fracture or impurities or the precipitation of undesirable compound or phase. Decreasing the grain size also is an effective way to increase ductility. When grain size is reduced, there are more grains with a greater number or rarely aligned slip planes for the dislocation in the grain. This provides more opportunity for some slip to occur in a stressed material. Thus, grain refinement provides an important means to improve not only strength, but also ductility and toughness. Many other straining mechanisms are safe at the expense of ductility and toughness. Fracture resistance also generally improve with reduced in grain size because the crack form during deformation, which are the precursors to those causing fracture, may initially be limited in size to grain diameter. The effect of grain size of strain is described by the Hall-Petz equation. Based on the independent observation and groundbreaking work of E.O. Hall and N.G. Petz in the early 1950s, this equals relate the effect of grain size in the yield strength of material. Weakening of grain boundaries. Exception occurs when environmental factors cause a weakening of the grain boundaries, like temperature, for example, can have a much greater effect on the weakening of grain boundaries than on the more regular array of atoms contained within the crystalline grains. As noted, when the temperature increases, there is a point at which the grains and the grains boundary exhibit the equal strength. This temperature is called the equicohesive temperature. Grain boundaries are stronger than the grains below the equicohesive temperature, while grains become stronger than the grains boundaries above the equicohesive temperature. The equicohesive temperature varies from alloy to alloy, but is typically about 0.4 to 0.5 times the melting point of the base metal in an alloy. When the temperature approaches or exceeds the equicohesive temperature of an alloy, the weakened grain boundaries become a source of the time-dependent deformation. The mechanisms of deformation are complex, but the important point is that creep deformation occurs continuously over time. Thus, continuous deformation caused by creep can lead ultimately to creep rupture. Creep and creep rupture can be the limiting factor in design of adequate section size for application at elevated temperature. In this case, creep stress and the describe rupture strength at the high temperature are important properties. Above the equal temperature, coarse grain specimen also exhibit greater strength than fine grain specimen because of the lower grain boundary surface area. Thus, larger grain size may be desirable in alloy from creep-resistant application. This also is why some high-temperature alloy are solidified into a single crystal. The grain boundaries regions are also susceptible to weakening by impurities. Grain boundaries are regions with many fault, dislocation, and void. This relative atomic disarray of the grain boundaries as compared to the more regular atomic arrangement of the grain interiors provides an easy path for diffusion-related alteration. Grain boundaries are thus preferential region for coagulation and segregation of impurities. Putting or embrittlement can also occur by preferential precipitation of absorption of environmental species in the grain's boundaries. For example, hydrogen embrittlement is associated with the diffusion and relative concentration of hydrogen to the grain boundaries. Okay, we next to the 3.2.3 cold working. Okay, cold working. If a metal is deformed at room temperature or up to approximately 0.3 km, where 3 m is the melting point on the absolute temperature scale, the microstructure becomes deformed due to cold working, also known as word hardening or strain hardening. During cold working, most of the energy is dissipated in the workpiece as heat. However, as much as 10% of the energy is retained as stored energy with the metal in the form of vacancy, dislocation, and stacking fault. The amount of stored energy increases with greater amounts of deformation and lower working temperature. Cold working greatly increases the number of dislocation. Normal dislocation densities on the order of 10 to 6 to 10 to 7 centimeter cubic. Centimeter are increased to 10 to 8 to 10 to 11 centimeter during cold working. During cold rolling, the grains also become distorted. The grains and their slip planes try to align themselves with the direction of rolling. The specific nature of grain distortion depends on the type of deformation process. Such processes include rolling, pressing, drawing, and spinning. With increased degrees of deformation, the amount of elongation increases in the direction of metal flow. With heavy cold working, the original grains are severely distorted to the point where they fracture into smaller grains. Heavy cold working can also lead to a preferred orientation or texture, in which the grains become oriented along certain crystallographic plane in a preferred manner with respect to the direction of the applied stress. Metal and alloy experience significant can change their property as a result of cold working and also as a result of heating the cold work structure. This change must be taken into account during forming operation, especially if the deformation is served as a deep drawing, for example, As a metal is deformed by cold working, the strength increase, the ductility decrease. Eventually, a point is reached where it is necessary to anneal the piece to allow further forming operation without the risk of producing cracks. In addition, some metal are strengthened primarily by cold working. In this case, it is important that the metal not soften possibility when placed in surface. Okay, next, annealing. Because the strength of the material increase due to wall hardening, the material become more difficult to deform further. Annealing consists of heating a metal to a specific temperature and holding it for a specified period of time, then cooling it using a specified series of steps at a specified cooling rate. Primary use of annealing includes softening metal spheres to or during fabrication process. Annealing as an intermediate step in the cold working process to reduce the internal stress in the material and increase its ductility so that it can undergo further cold working without introducing macroscopic defects such as crack. During annealing, there are three distinct processes can occur. First, recovery, which relieves some of the stored internal strength energy by rearrangement of dislocation into lower energy configuration without any change in the shape and orientation of grain. Second, resization, which is the replacement of the badly deformed cold walls grain by new strand-free grains. And the last one, grain growth, which occurs when some of the recycled grain grow at the expense of other recrystallized grain. This microstructural change during annealing have different effect on property. Grain growth is almost always an undesirable process because fine grain material offer the best combination of strength and ductility. During recovery, the strength and ductility are largely unaffected, but many physical properties are recovered to their original pre-cold working levels. During resization, strength decrease and the ductility increase, similar to that of the metal before cold working. Resization can occur either during annealing after cold working or during the deformation process at the sufficiently high temperature to help drive the formation of new grains. The latter is referred to as hot working. Recovery and resization are two distinctly different processes. At a constant temperature, recovery starts rapidly and then decreases with time. On the other hand, resization, which is a nucleation and growth process, starts slowly and then builds up to a maximum rate before rapidly leveling off. Accordingly, isothermal resization curves are typically sigmoidal in shape because there is an incubation period during which no visible resization occurs. During incubation, there is an irreversible coalescence of some grain, which grow until there is enough energy for it to attract enough atoms and become a stable nucleus for the one set of crystallization. Strain hardening parameter. Deformation during cold working begins in the grain interior once deformation is initiated. The moving dislocation in the grains interact with each other and with the grain boundaries. This makes continued yielding more difficult. The result is work hardening, and the work hardening effect continues to build with continued deformation and undesitalized grains. Work hardening can be described by the following empirical relationship in terms of flow stress: sigma F and plastic strain. Epsilon such that sigma F equals K epsilon F, where K is the strength coefficient and N is strength hardening exponent. From this equation, a high strength coefficient indicates a high initial resistance to plastic flow. Metal with a high K requires large machine for deformation. The strain hardening exponent, or N, is the slope of the stress strain curve after the tensile yield strength. It exists for steel. K increases with carbon content, while N generally decreases. Both copper and brass have a much higher work hardening exponent than steel. Both K and N are affected not only by chemistry but also by prior history and the microstructure. Work hardening is a measure of how the resistance to plastic flow increases as a metal is deformed. Typically, N has value of 0.1 to 0.5 for cold working, with 0 being a perfectly plastic metal. A metal with a high work hardening exponent but a low strength coefficient will achieve a high strength level after a large amount of deformation. Copper, brass, and low carbon steel are typically examples of metals that are cold worked to produce improved hardness and strength in the former part. The strain hardening of commercially pure aluminum. Cold working is an effective way of straining pure metals, which tend to be much softer and ductile than alloys. For example, cold working and annealing is typical for 1060 aluminum, which is commercially pure aluminum with 99.6% aluminum and some impurities. Products from 1060 aluminum include sheet and plate. This alloy is typically used in products requiring good resistance to corrosion and good cold formability, and where low strength can be tolerated, as in chemical process equipment and railway tank cars. The strength of 1060 aluminum is enhanced moderately by cold working. Standardized temper designation are used to indicate the condition of aluminum and aluminum alloy. Temper O is the soft condition. The H1 is a temper prefix that applies to products that are only strained hardened to obtain the desired strength without supplementary thermal treatment. Okay, we next to 3.2.4, back to Dr. Will's mystery. The good doctor discovered a process known as a solution heat treating and natural aging. He also designed an alloy suitable for straightening by this process in what is known as precipitation hardening. To explain, we call that Dr. Wilms subject duraluminum to an elevated temperature and then rapidly cool the alloy back to the room temperature. The strength of the alloy that increase over time at the room temperature. The first part of the mystery is to understand what is meant by a solution heat treatment for duraluminum and the other aluminum copper alloy. When the temperature is increased, the solubility of copper in aluminum far exceeds the solubility at room temperature. Thus, more copper can dissolve to the aluminum lattice at high temperature. However, when the alloy is rapidly cooled, the copper atoms do not have adequate time to move and form the space equilibrium state of aluminum copper solid solution with some CuAl2 phase. Instead, an unstable supersaturated condition is created after quenching. At room temperature, the solubility of copper in aluminum drops to a small fraction of 1%. And at this point, the copper solid is locked inside the aluminum lattice, but must precipitate out of the supersaturated aluminum lattice. In solution treating, the major outcome is to develop and maintain a supersaturated solution of copper in the aluminum lattice. The result is obtained by rapid cooling to room temperature when sufficient amounts of solid are trapped in the supersaturated condition. Sufficient solid are proximity to form zones. When these zones are small and more or less continuous, then the zones of precipitate solid are said to be coherent precipitation. Coherent zones are small enough to fit within the host lattice and thus cause straightening by distortion of the lattice. Eventually, coherency is the lowest when the precipitation zone is large enough to create its own crystal structure. And at this time, lattice distortion is relieved with some reduction in hardness and strength. Dr. Wilms' mystery could not be solved for several years. The condition of precipitation hardening were not understood until 1919, when the theory and practice of precipitation hardening in alloy were published by America and his colleagues at the U.S. National Bureau of Standards. This opened an era of the phase diagram and alloy development and commercial application of many edge hardened alloy. In addition, the zone of coherent precipitation are so small that they cannot be resolved in optical microscope. Detection requires the submicron resolution of the transmission electron microscope. The first experimental discovery of coherent precipitates occurred independently from X-ray diffraction studies by Andre Guiner and G. Peterson in 1938. The zone of coherent precipitation are now referred to as Guiner-Preston or GP zone. The increase in hardness with time is known as precipitation hardening or edge hardening. In zone 1, submicroscopic precipitate particles are being formed as the alloy attempt to reach equilibrium. Solid atoms diffuse through the solvent lattice and segregate to form a few very small particles, states in which solid atoms are grouped or rearranged so they can begin to form precipitate. This results in a slight increase in hardness. In zone 2, maximum hardness is reached. The solid atom move about form small particles attempting to form the precipitate phase. The precipitate phase remains coherent with the aluminum lattice. Strength increase significantly. Zone 3, the precipitates grow in size with continued aging and tend to become non-coherent. The loss of coherency reduces lattice stress, resulting in decreased hardness. Natural aging of alloy 2017. The modern day version of WIM alloy contains 4% copper, 0.6% magnesium, and 0.5 silicon. In addition to other alloying elements, and with the balance being aluminum. Products from include forgings, interaction bars, rod, wire, shape and rivets. Solution treating temperatures range from 500 to 510 degrees Celsius. During solution treatment, the temperature should be maintained within plus minus 6 degrees Celsius of the required treatment temperature. Quenching is performed in a water that is at room temperature and should be not allowed to drop below 38 degrees Celsius during the quenching cycle. Cooling from the solution treatment temperature to room temperature must be complete within approximately 10 seconds. Aging takes place at room temperature over a period of several days. Okay, example of other precipitation. Hardening aluminum alloy. Edge hardening aluminum alloy are commonly referred to as the heat treatment aluminum alloy, with few exceptions. Most commercial heat treatment aluminum alloy are based on ternary or quaternary alloys. Okay, next we 3.2.5, the other important strengthening mechanism. Dispersion strengthening. Dispersion strengthening is an active mechanism in alloy intended for use at intermediate and elevated temperature. It is in many ways very similar to edge hardening. The difference lies in the precipitates themselves. The tactile are chosen because of the thermal stability, that is, their resistance to practice coarsening or growth at high temperature. In contrast, the edge hardening aluminum alloy consists of precipitates that are not particularly thermally stable. Dispersion strengthened alloy are usually those that contain a dispersion of particles with extremely low solubilities and diffusion rates in metals. An example of a dispersion stranding base for high temperature application are the rare or oxidized used in producing oxidized dispersion strengthened or ODS alloy. This ODS alloy, the solubilities of both the rare earths and oxygen tend to be very low in typical matrix, and the diffusivities of the rare earth element are also slow. We next to dispersion stranding of copper alloy for hardening, controlling grain size, providing softening resistance is exemplified by iron particle in copper iron alloys C19200 or C19400, and in aluminum bronze C61300 or C63380, cobalt silicide particle in copper alloy C63800, for example, provide fine grain control and dispersion hardening to give this alloy high strength with reasonably good formability. Alloy C63800 offer an unalloyed tensile strength of 570 MPa and roll tempered tensile strength of 660 to 900 MPa. Alloys offering exceptionally good thermal stability have been deployed using power metallurgy technique to incorporate dispersion of fine Al2O3 particle in a basically copper matrix, which is finished process to roadware or strip produce. This family of alloy C15750 to C15760 can resist softening up to above 800 degrees Celsius. Hardening due to formation of martensite. Martensite is a non-equilibrium base processing a body center tetragonal or BCT crystal structure that form during a very rapid change in temperature. In general, metastatic transformation can occur in many types of metallic and non-metallic crystal, minerals, and compounds, just so long as the cooling or heating rate is sufficiently rapid. The basic mechanism and martensite formation involve the simulation rearrangement of many atoms, where is a series of individual atoms move a distance less than one interatomic spacing. This small but orderly movement of many atoms changed by lattice structure of atoms into a BCT crystal structure. CT crystal structure. That's all about the mechanical property and stranding mechanism from me. If you have a question, you can write below in a column section. Thank you.